sound okay. And I'm even recording, even better. Hope you all had a good weekend. Um, Thanks for getting all your assignments in on Friday. I've got about a third of them graded, and I will get the rest of them graded pretty soon. Um, Again, the bigger goal for that one is to get you thinking about what's actually going on behind the scenes with software engineering and why it's necessary. Also, to form your project teams. So if you put in I don't have a team yet. I'll assign you to a team soon and I'll let you and the team know. So if you're waiting, just be aware that that's coming. And let's talk about more of what software engineering is. And I guess the other announcement too. So you have that Git intro to Git thing is due on Friday, I believe. And what I will probably do is I'll release the second part of that in the next couple of days just so that you have it available to work on if you're ready to be working on it. The second part is using Git to set up your term project website, which so you'll be making a github.io page and a GitHub repository. And you're also going to be setting up a personal account as well. So you're going to have a personal portfolio if you don't have one already. And if you don't have one, it's kind of a good reason or a good, I guess, impetus to make one. It's always good to have a web presence up there. And the cool thing with Git is that it is free, or sorry, with GitHub is that it is free. All right, little green circle is here. And we are good to go. So last time we left off talking about software engineering in terms of, some of the problems that we saw. We talked about what makes good software, and I've been talking a lot about quality. If you remember from Friday, I know it was eons ago at this point. But with quality, one of the things that is going to really impact us are the stakeholders in the project. And I'm curious, without introducing it, if any of you have any idea what a stakeholder could be. This is oddly, oh, it's the aspect ratio of these slides, I forgot. So this might be a term that you may or may not have heard of at this point in your academic and or industrial careers, depending on where you're at. But what is a stakeholder for a project? Let's see if I can get us all thinking early on a Monday morning. Hopefully the stream isn't too far behind. I was having some weird lag issues. And to help you out with this difficult choice, there we go. So the bad thing about this one, so this is a Jeopardy 10-hour version. There are times when I throw that up in class, like if we're doing a lab or something, I'll forget it's on. I'll just kind of start letting it go forever. All right, good answers up here. Someone who is directly affected by the outcome of the project. Somebody who's invested money, the client and or company. Something. Yeah, these are all correct answers. So the interesting thing about stakeholder is that if you have no idea what the term means, you might think it's something related to budget or money or like a stock related kind of thing, right? That's usually what you hear stakeholders in terms of. In terms of software engineering, though, these are all correct, money and or time or effort. A stakeholder is going to be somebody who is invested in the project in some way. And invested, again, could be money, so you could be the CEO of the company, could be the clients. Again, they're investing money in there. It could be the engineers who are investing their time and effort. Could be the business manager, the customer center, so the people who interact with the clients. could be your quality team, it could be the intern that's hired for the summer to make a little checkbox on a GUI function a little bit quicker or something of that nature. So basically a stakeholder, sorry, I went the wrong way here. A stakeholder is anybody who has their fingers on the project, basically. So anybody who is directly affected or works on the project. So these are all great answers. And it's a little bit of a different perspective from what we might kind of expect, right? We don't think that, every single person who has touched the project in some way is a stakeholder, but they are affected by it, right? Depending on the project setup, you might have a design team or a requirements engineering team where their job is the first month of the project, write up all the requirements because they figure out what the customer wants, and then they're done, right? They move on to the next project and write another set of requirements, depending on if your company's set up that way. They are still stakeholders, even though their input is no longer really actively moving the project forward. They may have done their job already, but they're still stakeholders. The business person who is, kind of constructing the sale of this project, maybe they're reaching out to the marketing team to figure out what the customers want in terms of this project. They're a stakeholder too. Basically, they're going to influence the project. That's what makes a stakeholder. And why I'm talking about this in terms of quality and in terms of the software engineering side, all of these people's inputs will have an impact. So it's good to manage that. All right, so yeah, good answers there. So this is kind of what I talked about here. We get some nice 90s era clip art for this. But we have multiple users in the loop here, right? So your customer is going to be the person or company buying your product. They're sponsoring it, right? They are either directly or indirectly paying for it. They get a say in what it should look like, right? You have a developer. They're going to be the ones writing the code, building the system. And in this very, very simplistic view, the developer would be anybody in the engineering team, for instance, whether you're writing code or tests or models or requirements. This is all going to be one large group of people. But the system will be built by them. They'll have input. We also have a contractual obligation too, right? The customer is paying us X dollars for a product with the assumption that they are getting a product specified like they want. So we have an obligation to make that. Otherwise, we get into legal trouble. Then we have our users, which are the worst thing to happen to software, obviously, the users, because they break things and they never know what they want. But they need software to operate. Customer and the user, or the customer and the client, whatever you want to call this group of people, they might not be the same, right? I might be a game publisher paying a developer to build a game, and the users are going to be the people buying the game, right? So customer and the client, not always the same people. Another view you might have too, these might all be internal to a company, right? The users, the customers, the developers, they might all be building something in-house, so it's not necessarily something going to market, but maybe it's a tool that's helping our engineering process or, any process team, right? Or any project team. So just be aware. You're gonna have a lot of people to deal with in your engineering life, which is kind of why we make you work in project teams, honestly. 1 second, I'll be right back. Sorry, forgot something. I probably could have talked to you the entire time I was gone. But yeah, we will come back to stakeholders because it's going to kind of illustrate the types of jobs and responsibilities you can pick in industry. All right, looks like everybody's still here. Nobody disappeared while I was gone. Fester leaves the room, it means everybody can leave, right? Alrighty, so with our approaches here to building software, we know the people that are involved. And I keep clicking off the screen, so I keep losing the chat. We also have to figure out how we're going to define a system. So let's say that we're at the very beginning stages of constructing a project. Or we maybe have a customer that's going to pay us to build something, and now we have to figure out what that thing is going to be and how we build it. And if it sounds like I'm overcomplicating the process of making software, we're adding layers of complexity to make it more rigorous and make it better effectively. So what do we care about? We care about what hardware we're going to need. We care about what software we're going to need. Are we going to buy it? Are we going to build it in-house? Are we going to hire 30 interns to build something quick and then hopefully either hire those interns or fix the code? Is this software going to have to interact with people? Do we have to interact with people? What's the system going to do? We have to consider that very early on. Then we have to figure out what activities we have to perform. Is this system going to be reaching out to the network? Does it need to be rigorously certified because it's going in a vehicle or an airplane? Does it have to, is it have to be very highly secured because it's holding sensitive data, right? What activities are going to have to be performed with this thing? What objects maybe do we need, right? Start thinking about like what classes are going to be put into this if we're doing it in Java. What objects are we going to instantiate as part of the system? Will there be a user class? Will there be a game display window that's going to show our game or our app or whatever it is? What do we need basically? And then we have to figure out the boundary of the system, which is what we're going to talk about now. Basically, these should look pretty similar to kind of your, standard approach to making software, but again, with a little bit more rigor, right? Let's start actually giving ourselves a checklist to go through. That way we don't have to do, like, we don't have a lot of wiggle room for error, basically, is kind of what we're looking at. All right, so this is basically just kind of what I expanded on earlier, so I'm not going to reread through these already. But just to kind of highlight activities and objects, since this was the second one here, they're going to be part of your system, and we should figure out what they are early on. If you have to add a new activity, add a new object, add a new thing to your system, it may impact everything else later down the line. So it's really good to try and figure out early on exactly what the pieces of this software puzzle are going to be. The system boundary, I kind of didn't go into as much detail, but it's going to tell you where your system stops and ends. And that's very important with software because you don't want to overreach and you also don't want to basically underperform because you're either doing too much with your system or you're doing too little. And that's kind of a little hand wavy type of gesture that I'm doing here, but it's really good to know where to stop with your software. I've got some pictures of what this could look like in a moment here. The other one that is super important though is the relationships. So the relationships between objects, between systems, between actors, which are going to be people invested in using the system. How does your system interact with them? Like, let's say that I have a phone app that I'm developing and it's going to reach out to a cloud provider to give me data, right? Maybe it's like a phone app tied to Google Maps or, you know, Microsoft Bing Maps or Apple Maps or whatever your favorite map provider is. I want to get all the local restaurants in the area that are serving, maybe good Thai or good sushi or something like that. Well, my app, it's not going to have all that data locally. I don't have the entire internet on my phone, right? But it's going to reach out to this cloud provider, cloud service, or remote API or whatever it is. The relationship here is how are we sending data and receiving data, right? What format are we sending it in? How quickly does it come in? Basically, you just have to kind of think of everything your system has to do beforehand. And I talked about system boundaries, so here's a great example of a boundary. And again, more lovely clip art. Gotta love old slides that you don't want to modify because you like them and think they're cute with their square aspect ratio. Here is your respiratory system in general, obviously. The boundary of your respiratory system is going to be here, right? So this little greenish line, which looks pretty similar to all the other lines. You have the lines around your lungs there. But what do we care about in this? Let's pretend this is a system. I mean, it is a system, but let's talk about it as a system in terms of software engineering. All of the entities or objects or things that go into the system. We have to deal with particulate matter. So you're breathing in junk from the atmosphere, right? Oxygen, carbon dioxide, nitrogen, all of this stuff that is just kind of floating around in the air or that you ingest. It's something you would have to deal with. Your body has to deal with that, right? We also have your nose, your mouth, your trachea, your lungs, your alveoli. Basically, everything that makes up this system is an object of some type, right? It doesn't matter if it is water particles in the air. It doesn't matter if it's your lungs. It's still an object. So these are the things that we have. And if you start thinking of your software systems, it's like a collection of objects. Sometimes that helps the mental processing kind of move forward if you're, trying to specify a system and what it is. So we have objects. Objects do activities, right? So what is an activity for a respiratory system? Inhale, exhale, filter, transfer. These are all, if you kind of think of them, they're basically verbs, right? So they're doing something. That is your activity. A mouth or nose inhales gas, right? So you have an entity, mouth, activity, inhale. You could include gases as an entity as well, but basically, we're doing something with the system. The important thing to note here too, and why I'm kind of sticking on the slide for a little bit, we have a very clearly defined boundary for this system, right? We're not going to leverage the brain, or we're not going to leverage the armpits or any of our other cardiovascular systems in here to do respiratory things, right? That's their job. We are not going to be inhaling gases from our heart, right? So we know exactly what the system is doing. We know exactly which objects are coming into it. We know exactly which objects are going out of it, and we know exactly which activities are being performed on that. So it's kind of an interesting example of a system. And honestly, it's kind of why a lot of our algorithms and computing technologies are modeled on biology, because they're very good examples of systems. If we get towards like search-based stuff, there's a lot of biological inspiration out there. It's kind of cool. But that's obviously not a software system, right? It's a human system. What about actual software? A nice boring work environment. What about delivering a paycheck to a person? That's a great example of a system. And you're going to see here, when we start talking about computer software and hardware as a system-based approach, what's the difference? It's just kind of wording, right? So a lung is an object, a computer is an object, a piece of mail is an object. Everything can be an object, right? So this is a little bit of an outdated view of paycheck systems, but again, it's kind of a nice little example. I don't know how many of you still get paper paychecks. I guess depending on if the system hasn't been updated since the late 90s, you might still be getting them. Probably direct deposit these days, though, right? Let's say you go to work and you want to create paychecks. So you want to pay somebody for their time. Well, there is an entire category of systems for this. It's going to be ERP if that's going to be your jam. But let's say that we want to create a pay stub for a person. So we have a computer. This computer is going to be checking the personnel logs. What are their hours? Are they salaried, non-salaried, all that fun stuff. And it's going to generate, here is your monthly check from us for your work you did. Good job. You did that. Well, what is the system actually doing? It's going to be some kind of an internal system, and you're probably going to see figures like this again in the future. So these little dashed lines for an oval, this is going to be your system boundary. Anything outside of that boundary will be an external entity or actor. Anything inside that boundary is part of the system. So this system has a date validation application of some kind, right? Did you work these hours in this range? You're going to have a calculation where, based on your current pay rate or salary, you will get this amount for this range of dates, assuming it's valid. And then it's going to print out the check. Then, again, update this mentally for current days. This is going to create an e-check, or it's going to create a wire transfer to your bank or something like that. That's going to send information out to some external entities. So the entire boundary of the system is only concerned with figuring out what hours you worked. Is that correct? Create the check if it's necessary. So everything happening internally here is part of the system. Everything external is outside of the system, right? So the computer entering data is not strictly part of this system. The mailroom where you go pick up your check is not part of this system exactly. There's some kind of external entity that interacts with it, but they're not. If we have to make an update to the system, the computer's not going to be affected, the mailroom's not going to be affected. It's just internal here. And again, with this notion of a boundary, we can know exactly the format of data coming in, the format of data going out. Everything internal could be updatable, right? It's not going to impact to the outside entities. So that's just kind of a high-level description of a system, right? And again, system is a generic term. Take these images, pictures, swap them out for whatever you want. Your phone app, right? Phone could be an external entity, but if it's an amazing calculator doing non-Euclidean calculations or something like that, it's all the magic's happening inside. You can install it on any phone. You can have any user using this thing, but all the magic's happening inside the system boundary. All right, so we have a notion of what a system is. We know what objects are. We know what relationships are, hopefully, at this point. We also can have system dependencies too, right? So a system doesn't necessarily need to be all-encompassing. We can have subsystems. We can have systems dependent on other systems. Maybe they're not one inside of the other. Maybe they're just separate things that depend on each other. If any of you are in the the business of like web applications or anything like that, might be aware of the term microservice. That's the fun, newish, and exciting development task. Basically, have a bunch of little mini sub applications that all kind of depend on each other rather than one big monolithic application. These are all interrelated systems, right? Microservice A is going to take in data, format it, send it out. Microservice B is going to take that data and do something else with it. Right? We can model our little ERP system here as a collection of microservices. Right? We might have a little tiny date validator, might have a little tiny calculator. These could all be little tiny subsystems that all depend on each other. Basically, the thing with systems and object definition is it's all relative, right? It's all up to you as the engineer on how you want to specify things. Do you want the boundary to be here? Do you want the users inside of that boundary? Do you want them outside of it? We have a lot of wiggle room, a lot of play, and there's going to be a lot of trade-offs either way. I think I mentioned this before. This class is basically learning about all the trade-offs and decisions we're going to have to make as engineers. And it's a lot of fun. So here's another example of a system. Now this one's layered. This could be some kind of a data collection system, basically. So think of like you have a bunch of remote sensors, say all over your house, collecting temperature data or something like that. Or maybe around the city collecting air quality indicators or something like that. So this is going to be a remote data collection system as a whole, right? So we have a little tiny internal system that is basically going to handle data collection, right? So it might be a bunch of distributed remote data systems, right? Then we're gonna have to bring all that data together. Well, we have a calculation system to kind of fuse all these readings into one cohesive model. But this calculation system is going to depend on communications, right? If we have a bunch of little spread out nodes all over the city, they might need Bluetooth or Wi-Fi or GPS connectivity of some kind. Although if they're little tiny sensors, it's probably going to be like a mobile, a mobile phone type of chip on there. We're going to have to manage all this data. So if we're getting data, calculating, communicating, we're going to have to manage it with some kind of a database system probably. And then we have to be able to generate reports for this thing too. Otherwise, we're not going to be able to understand our data. But if you have a bunch of raw tabular data, unless you're intimately familiar with that data, and you can see the trends mentally, you're going to need reports and graphs and all kinds of easy to digest figures. So this is a layered system, right? They all depend on each other here. Okay, good so far. Enough talking about systems as a whole. Let's actually start talking about the exciting topic of software engineering. And I can't say that with a straight face. The important topic of software engineering. How's that? All right, all good so far. Everybody on board with systems. Again, it's not the most exciting topic, but it is very important for your future career, so I'll let you know that much. All right, if we're all good with that, let's talk about the steps that we have to do. This will be variable depending on your engineering process. This is the standard basic way of building software. So the first thing we have to do is figure out which requirements we need. And requirements are going to be prose, or basically like English or whatever your language of choice is, spoken language and written language of choice, not programming language. Basically, what is the system going to do very, very specifically? And you'll have an assignment where you have to define requirements for your project. But let's define them and then let's analyze them. Creating a requirement, say, let's define requirements for the perfect cup of coffee. We need water at a particular degree. We need a certain grind of coffee bean. We need a certain type of coffee bean. The coffee bean has to be ground up specifically and placed into a filter. The water has to be run through it for X seconds. Give it a little stir. I'm kind of bastardizing a French press and a normal drip coffee with this one, but basically we have a process that we follow. The requirements are going to capture one specific piece of this process. Coffee ground has to be very finely ground to a sand-like texture, something like that. We have very, very specific notions of what a requirement is. Basically, you're going to define these things, and then you're going to come back and go through them over and over and over again until you're happy. For this class, we're going to do it once, maybe twice, depending on how the semester goes. All right, so we have a long list of documents that specify our requirements. Then we're going to get into our system design. This is where we start figuring out how the pieces of the puzzle kind of fit together, right? Which systems do we need? What are their inputs and outputs? How do they interact with each other? What are the objects? What are the entities? Basically, you're getting from very specific list of things the system should be doing to kind of an idea of what it should start looking like, right? I'm going to just pop all these up here so that you know what you're getting into. So right now we're at system design. We're specifying out what it should look like as a whole. Then we start getting into program design. This is going to be, I'll leave this right here so that it makes sense. This is going to be where you start figuring out how to actually implement the thing. All right, so you have requirements. You have very clear specifications of what to write to. You have an idea of maybe the architecture of the system, how pieces fit together. Now, how are we going to implement this? This is going to be like making class diagrams in Java. This is going to be making some of the various system models that tell you, okay, this system will be instantiated here. It's going to have X, Y, and Z parameters. These parameters will be, instantiated in such a way, and that information can be passed on to this other object. And basically, you're kind of, again, high level figuring out what your system is doing, but at a finer grained level. Is this UML phase? Basically, yeah. System and program can be UML-esque. It's just kind of the granularity of what you're looking at. So program design would be more like your common class diagrams type of thing. System design would be more like an architecture model or a component model or something like that. High level, low level, basically. All right, then we write the program. This is the phase where there should be absolutely no question of what you're doing, okay? I'm going to come back to this over and over and over again. Writing the program is the easy part of the engineering process. Whether you're comfortable programming yet or not, if you know exactly what you're supposed to be doing, it's just a mechanical process, right? You know how to write a for loop. You know how to pull information from a database. You know how to develop a GUI for the user to interact with, right? There's not a lot of mental effort that has to be made at this phase. All of the hard work, honestly, is up here. This is the time that you spend thinking about your project, what it's going to be doing, in exactly what the inputs and outputs are going to be and what it should look like, right? This is all of the mental effort here. Writing the program is just a pure technical activity. Now, is there some, wiggle room with like kind of the soft things like user interface designer? We can optimize this particular module by swapping out our algorithms to do something a little bit more performant, or we're taking advantage of the GPU. Absolutely, we can do all that stuff. But again, it's something technical that you can very easily do. If I give you, now let's say I'm talking to each and every one of you, I come up with a list of requirements, right? I have a program that I want to do this, 50 requirements that it has to do. I can guarantee that I could give that document to every single one of you. You could take however long you need to develop this software. You would all probably have different approaches for writing the code, but you'd probably get something pretty similar, right? And all the really hard mental work is at the beginning phases when we actually have to figure out what we're going to be making. Okay, so basically, if you're not strong with programming yet, don't worry, you will be. And if you're really good with requirements analysis and design, that's the hard stuff. Writing the programs is the easy part. All right, then we have all these other phases too. We have unit testing. We have three plus areas of testing. Unit testing is testing your functions, testing the smallest pieces of code that you can to make sure they're doing what you expect them to do. You have integration testing, where you're taking together pieces of your software, putting them together, making sure that software is still doing what it should be doing. Example here, because this concept didn't really make too much sense last semester for some of the students. Unit testing is like, let's test a function, make sure that the input is correct, make sure the output is correct. Integration testing would be like, let's say you have a project team for your term projects. One of you builds a particular section, another person builds their own thing. Separately, they're fine. They test correctly, right? Then, because you're a project team, you have to bring your source code together. Is it still doing what it should be doing? And interestingly, there always tends to be interactions with your code when you start bringing things together. So we're integrating our software. And there's a lot more to it than just making sure the inputs and outputs still work. You also have to go back and make sure the old tests still work, which is regression testing. There's lots of testing. Then we have system testing where, okay, we have our integration pieces are done. Integration also could be like release testing where you have a beta that you're ready to ship out. You could be integration testing for like a release candidate. Just in case if you've heard these terms before, they're kind of malleable in what they're looking at depending on your project. You have system testing where all of the pieces are now together. It is probably in its environment that it should be in. Let's test the system as a whole. These are all going to be different test cases too, more or less. Then we're going to deliver it to the customer or the client, whoever's taking it on. We're going to test it with them, make sure they're happy with what they got. Then the last phase is maintenance. We have to keep supporting this project for however long we're under contract, right? This might include bug fixes. It might include software updates. If you're a game company, it's going to be a day one patch, obviously, right? But think of software that you see on like GitHub or on the internet. You see people are maintaining it for years and years and years, right? You see, hey, this particular JavaScript library got updated. We've now updated our project to support it. Or we're now supporting the newest version of Mac OS or Android, whatever version we're at with Android these days. So basically, software engineering, you think you're just going to be writing code, but that's just one little bullet point here. There is a ton of stuff we have to do with software engineering. And I don't want to make it sound horrible. It's a lot of fun. It's a very rewarding field. Just make sure you get good ergonomic keyboard and good typing processes down early on. Otherwise, you start ending up with carpal tunnel type things. little bit of a divergence there. Okay, so that's all the activities we have to do. Who are we going to be working with? I'm going to pop all of these up as well. Some days I'm in the mood for animating them and sometimes I'm not. These are going to be your roles in the project team. And depending on your environment, you might be fulfilling multiple roles here. You might be hired on as a particular role, so you might be hired as a tester. You might be hired as a programmer. Maybe you're not a great programmer, but you're a great software designer, right? So these could all be different roles that you could take in a team. And depending on your project, you could satisfy multiple roles here. So what are we doing here? Requirements analyst. Work with the customer to identify and document the requirements. What does that mean? You have to talk, actually talk to other people. Sounds awful. And figure out what they want. So you're the person that is actually figuring out how this software is going to look, what it should be doing, and what its requirements are. Then it's going to be your job to write that down in such a way that everybody who is a stakeholder in this team can understand what it's supposed to be doing. So there's that role. We have the designers, basically take these requirements and start constructing software at a high level. Programmers should make sense. You're taking that and making it a functioning program. The testers, I think we talked about this in the ethics phase. Testers should be a completely different person, a completely different group than the programmers, right? Don't check your own code. Now, is it okay to unit test your own code? Absolutely. Those are simple things we can automate. But the real, big tests that are very, very important to get right, different testing group. We also have trainers. Maybe you have to train your users on how to implement the system, right? If you're good with working with people, we can write training plans. We can write, video modules. We can go out to customer sites and try to get them to, use the software, train them, things of that nature. Maintenance team. Maybe bugs crop up after release. You have to go back, fix the software, re-release it, go through multiple phases of the design process again to fix that. I'm going to lump these last two together because I honestly, in industry, I never heard the term librarian. I think it's kind of antiquated probably at this point. But basically, you have a configuration management team who is going to be in charge of maintaining the systems that you put your code into, that you put your requirements and your models into, you put your reports into. It's basically, we're going to be using GitHub for our configuration management this semester. But you could be using Subversion, you could be using something very expensive like Atlassian or MKS is another one. Basically, these are the people supporting the development teams. And the interesting thing about documents like requirements or design documents, they can be version controlled just like software can. All right, what roles will you play on a development team? Basically, this is kind of a, free-form list. You have analysts, designers, programmers. You kind of see where these people's roles fall in terms of what actually has to be done. This is the same list as before. Here are the people from the prior slide. Analyst might be doing requirements and system design and maintenance. The tester could be doing unit testing, could be doing integration testing, could be system testing and maintenance. What you kind of see is that depending on your role in the company, you could actually fulfill multiple software development roles as well. But kind of the key thing here too, which is at least I think interesting, again, depending on your company, you may have some maintenance responsibilities too. So just be aware roles can be free form. Yeah, we have 10 minutes and a lot of slides to go through still. All right, good so far, I hope. And I'm going to skip that slide, but let's talk about this one. The things we have to deal with in terms of software engineering, I think, are kind of an interesting thing to talk about. Now, I've got this Wasserman 7 key factors. Basically, this is one of the big people in the open source initiatives in the computer-aided software engineering or the CASE tools. Basically, pretty big in the ACM, I think. So what do we care about in terms of software? We care about the time to market. So the time from project inception to when clients can start buying it. right? We need a very quick turnaround for that. Computing economics have changed. So the last slide you saw a quick blip about the 70s. Things have changed, right? We don't have mainframes anymore. Mainframes are now basically cloud computing, but everybody has a device in their pocket. Everybody has a laptop. Everybody might have a tablet for work, right? Whatever you need. Um, Computing has gotten significantly cheaper. Desktops have gotten more powerful. These actually impact the software we make, right? Same with networking capabilities, right? We are now dealing on a global scale with our programs. If I put up an application to the Google Play Market or the Google Play Store or the, Apple Store, people around the globe could buy that and use it. And now say I'm not just supporting 10 people, 10 of my friends who like the world's best fart app. Now people around the world can download that, and maybe it has to be localized for their environment. Um, maybe it's not allowed to be sold in particular regions. There's lots of considerations here. We have GUIs now, right? So GUIs are no longer buttons on a desktop. Now they're responsive phone designs. They're touch screens, capacitive sense where you can have pressure on there. Object-oriented technologies, hopefully you're all getting a taste of in your intro to Java classes, but that was a new paradigm shift for market or for software engineering. Different software development models we'll talk about. Basically, kind of think of how computing has changed over time, and think of the fact that software engineering as a discipline has had to change along with that. Right? It's probably mind-blowing in the 70s that you can have more than one person using a computer at the same time. How the hell are we going to design software to support that? Right? We're going to have a million race conditions that we have to deal with, right? What about all this object-oriented stuff that's happening? Okay, you're telling me that my procedural basic program that starts at main and it ends at the end of main, now I have to support user events and callbacks and all this kind of stuff. It's incredible what we have to deal with as software engineers. But basically, this is all going to influence how you develop software. So how do we handle this? Well, we're going to handle it with a lot of abstractions. Basically, we're going to look at things like UML modeling, right? We'll prototype things. Maybe our models that we create, we're going to have design patterns that we follow, or we're going to look for anti-patterns. Design patterns we'll get to at the very end, but basically that tells us how you should be developing good software and what to watch out for if you're going down the bad software development phase. One of the great things we can do, though, is reuse, right? We've talked about reuse in kind of a negative light so far because there is Therac reused old code, the Ariana 5 rocket reused old code. We didn't touch on that really, but the issue is not reusing code. Reusing code saves you a lot of time. It's reusing code without going back and checking to make sure it's still valid, right? So basically, we have a lot of tools that we can use to make software engineering a good and rigorous process. All right, so abstraction. Kind of talked about this briefly a moment ago, but what is abstraction? You have all gotten a taste of abstraction with Java when you start using some of their baked-in classes, right? Like if you instantiated a tree or a linked list or a queue or something like that, you're abstracting the notion of a queue. I'm calling, you know, x equals new queue, but a queue is basically a whole list of objects with pointers and all kinds of crazy stuff behind the scenes. You're just dealing with the abstraction though. Same thing happens for software engineering. Let's say that a client wants an electrical device with a sensor on it, right? So we want to sense humidity of the air. Well, that sensor might have a water sensor, it might have an air sensor on it, but all you see is the electrical device. This is the abstraction. We're going to have abstractions like this in our processes. The goal is to hide the details where they're not necessary. Save the details for another document or the user that needs to know that. So with sorry, I'm trying to make sure we get everything we need to today. What we're kind of going to see, and let me just summarize because there's like 10 slides left and I want to be done with this as of today, I think. We're going to see that our software engineering processes are different based on which company you work in and which project you're working on, right? Here I've got prototyping. Not every project does prototyping, but they do it where necessary. Maybe your client wants a very quick view of what you're getting at. Let's make a little demo. Let's make a little prototype. And by looking at this prototype, you can figure out, hey, actually, we really hate these requirements. Let's get rid of them. Or let's update them to be, in a little bit of a different format to better be what we want. Developing requirements, developing systems is a very iterative process. Sometimes you have a very rigorous formal process you follow, and that's it. That's great for big monolithic systems. But if you're in a very fast-paced, free-form environment, maybe something like prototyping is helpful. We'll talk about Agile later on, where you have a lot more flexibility in your development processes. So let's see. Yeah, so we're pretty much done here. Last thing to really talk about is, I mentioned system architecture and modeling and abstractions. Here is one example of what a system architecture might look like from a UML perspective. Basically, here we have, and this is going to look like gibberish if you've never really used UML here, but we have a architecture of an entire system, right? We have a web server, we have a load balancer, we have 2 app servers, we have a database server. You look at this, it's probably a web application of some kind, right? And because we have a load balancer, there's probably going to be a lot of people using this thing. Do we have the details in here? No, we don't, right? We know there is some web form component. We know there's a dispatcher for the load balancer. We know each app server could have a monitoring bit where even in our monitoring bit, we can have abstractions of what it's supposed to be doing. Kind of the key takeaway is that just depending on where you are in your process, you might be looking at different levels of detail. I'm not trying to go too far off the rails here with this little talk, but I wanted to give you an actual sneak peek of what some of these abstractions look like. If you look at this, the programmer is probably not going to know what to do with this, right? Okay, you want to tell me you need a web server and a load balancer and a bunch of app servers. Great. What are they doing? I don't know. Well, I know I've got some web forms in here. Maybe I've got more documentation on what this web form does, right? Maybe I have a list of requirements for what this monitoring phase is supposed to be doing. I've got a document somewhere or a model or something of what this database server is doing, right? Is it SQL? Is it Bigtable? Is it MongoDB? Are we using a graph-based language, right? There's not that detail here, but we know the pieces we need and how they interact. So it's good for that. Kind of the key takeaway is we're going to have a lot of models to deal with, we'll have a lot of abstractions, and a lot of processes to talk about. So that's going to be it for Intro to SE. Next time we're going to talk about some of the different models that are out there. That will be Wednesday. Anyway, any questions from today? Kind of skipped through a few things here in the end. That's basically just kind of a through the ages of software engineering type of view. But everybody good for today? Hopefully. Everybody tune me out and gonna catch the video on demand later on. Let's see, what are we gonna do for outro music? Stormy ambiance, that'll work. All right, how will people know their groups for those who didn't find one? I will email you. Yeah. Basically, the process, so if just so that you're aware, I'm making breakfast. I hope it's good breakfast. If you did not find a project team, basically I'm going to look through the teams that were formed and I'm going to look at the topics. And I will contact those teams, make sure they're okay with taking on a new member, and then I'll assign you. So be a couple of days at least before you find out, but you will get those very, very shortly. So, you all have a wonderful day. I will see you all Wednesday, and bye-bye for now, I suppose. Yeah.